In this video, I will share an experiment to determine capacitance of a capacitor using flashing and quenching of a neon lamp. A neon lamp consists of a small glass bulb filled with neon gas at low pressure, and it is fitted with two electrodes. When electrodes of neon lamp are connected to a variable DC source, the stray electrons available in the bulb get attracted towards electrode connected to positive of the battery. With increase in applied DC voltage, speed of these stray electrons goes on increasing, and at a particular high voltage, energy of electrons becomes sufficient to ionize the neon gas molecules. At this stage, the neon lamp begins to glow red due to excitation and de-excitation of neon gas molecules. The value of applied voltage at which neon lamp starts glowing is called flashing potential of neon lamp, and it is about 180 volt. Due to ionization of neon gas molecules, a large number of electrons reach the positive electrode of neon lamp and the lamp becomes conducting. If the potential across neon lamp is not increased beyond flashing potential, the potential starts reducing and the lamp ceases to glow when potential gets reduced to substantially low value. The voltage at which the neon lamp ceases to glow is called quenching potential of neon lamp, and it is about 130 volt. Suppose a parallel combination of a capacitor and a neon lamp is connected to variable DC supply about 0 to 250 volt. When DC supply is switched on, charging of the capacitor starts. If supply voltage is slowly increased up to flashing potential of neon lamp, say V1, then the neon lamp begins to glow. If the supply voltage is not increased beyond V1, the capacitor starts discharging through the lamp and the lamp continues to glow for some time. As the potential across the capacitor becomes as low as quenching potential of neon lamp, say V2, the neon lamp ceases to glow for some time. During the time neon lamp does not glow, the capacitor continues charging and the neon lamp again starts glowing as the potential across the capacitor reaches flashing potential of neon lamp V1. In this way, the process of flashing and quenching of neon lamp repeats periodically. The periodic variation in potential across capacitor can be represented in the form of a graph. In this graph, T1 represents the time during which the neon lamp keeps glowing and the capacitor discharges to voltage V2. And T2 represents the time during which the neon lamp does not glow and the capacitor charges to V1. Thus, T1 plus T2 represents time gap between two consecutive flashes of neon lamp. As T1 is time during which the capacitor discharges from voltage V1 to V2, so we can write V2 equal to V1 e raised to power minus T1 upon CR. As T2 represents time during which capacitor charges from voltage V2 to V1, so we can write V1 equal to V2 divided by 1 minus e raised to power minus T2 upon CR. Using the values of T1 and T2, time gap between two consecutive neon lamp flashes can be proved to be directly proportional to capacitance of capacitor used parallel to the neon lamp. Thus, graph of time gap between two consecutive neon lamp flashes versus capacitance of capacitor must be a straight line. This is the required circuit diagram to determine unknown capacitance of a capacitor using flashing and quenching of a neon lamp. Here, X represents unknown capacitance of a capacitor that is to be determined. Let me introduce the apparatus. These are three capacitors connected parallel to each other, and this is neon lamp connected parallel to the capacitors. This is the capacitor, the capacitance of which is to be determined. This is variable DC power supply. Without connecting the capacitor of unknown capacitance, take only the first capacitor of capacitance C1 into the circuit. With the help of this knob, go on increasing voltage till the neon lamp starts glowing and immediately stop further increasing the voltage. Note time taken for 10 flashes to complete and reduce the voltage to 0. Take only the second capacitor of capacitance C2 into the circuit as done earlier. No time taken for 10 flashes to complete and reduce the voltage to 0. Similarly, note time taken for 10 flashes for capacitor of capacitance C3 and for all other capacitor combinations. Now connect the capacitor of unknown capacitance to the specified terminals. Take only the first capacitor into the circuit. Now the capacitors of capacitance C1 and unknown capacitance X are in the circuit. Note time taken for 10 flashes to complete and reduce the voltage to 0. Similarly, note time taken for 10 flashes in case of all the other capacitor combinations. Using the observed values of time taken for 10 flashes in first part of experiment when capacitor of unknown capacitance is not connected, calculate time gap between two consecutive flashes for each value of capacitance and plot a graph of time gap versus capacitance values. Similarly, using the observed values of time taken for 10 flashes in second part of experiment when capacitor of unknown capacitance is connected, calculate time gap between two consecutive flashes for each value of capacitance and plot a graph of time gap versus capacitance values on the same graph paper. Corresponding to any value of time gap, draw a horizontal straight line parallel to capacitance axis so as to intersect two straight line graphs at points A and B. From points A and B, draw perpendiculars on capacitance axis and note capacitance values corresponding to points A and B as CA and CB. Calculate unknown capacitance as X equal to CB minus CA. Thank you.